Now, when looking at titrations of weak with strong, it's actually kind of interesting to take a look at what's going on along the pH scale, because there are some changes that are occurring that have some interesting sorts of properties in terms of what's in solution and the mathematical equations that describe them. So I'm going to go ahead and do an example of this to give you a sense of what's going on. This right here is the titration of a weak acid with a strong base. We have to ask ourselves what we know to be a fact, for example, about the equivalence point here. This equivalence point is occurring where I have converted all of the acid into base. So this is a beaker filled with only weak base. Well, what do I know about that? What does the pH have to be? Well, does the pH, can it be less than 7? Can it be more than 7? Is it 7? Don't make this complicated. This pH right here is the pH of what's in this bucket. What's in this bucket? Well, that's a weak base. Well, weak bases have what pH? Oh, I guess a pH greater than 7. So we know for a fact that when I titrate a weak acid with a strong base, that it starts with a pH below 7 and doesn't end up at pH 7. It ends up at a pH at the equivalence point, which is above 7. It's also true that if I do the other titration, a weak base with a strong acid, that at the equivalence point, the pH of the solution is less than 7. This may seem obvious as I'm saying it to you here, but when you're doing problems on tests and it says true or false, the pH of a weak base titrated with a strong acid at the equivalence point is greater than 7, equal to 7, less than 7. It kind of blurs. But you have to understand that in that titration, the weak bases all become weak acid. Weak acids are weak acids. Their proton equals Ka Ca to the 1/2 is a value less than 7.